Okay, in this lesson we're going to talk about stretching, shrinking, and reflecting the parabola. So we're going to start by taking a look at g of x equals 2x squared, and you can see that we have a coefficient in front of our x squared. So we're going to compare this function with the parent function y equals x squared. Hopefully, from the last lesson, you have a really good idea of what y equals x squared looks like, and you can plot it on a coordinate plane fairly quickly. Hopefully you've gotten used to graphing those parent functions, y equals x squared, over and over again, where you know what the inputs and outputs are on a standard -10 to +10 x axis and a -10 to +10 y axis. So we're going to start by looking at g of x equals 2x squared, and then we'll compare that table and the outputs with our previous graph, y equals x squared. So we're going to start with -3, -2, -1, 0, 1, 2, and 3 as inputs into the function, just like we did on the last lesson. We're going to choose a few negative values, 0, and a few positive values to put in. Remember, x is our input, g of x is our output. So when I put a -3 into this function, I know that -3 times -3 is 9. So in the parent function, when I put a -3 in, I get a 9 out. But what I'm doing now is I'm taking that 9 and I'm going to multiply it by 2. So that gives me 18, because 9 times 2 is 18. I'm going to do the same thing, putting a -2 in. When I put a -2 in for x, I have -2 times -2 is +4. 4 times 2 is 8. So let me over here write what we've done is we put a -3 in, and we got -3 times -3 is 9, multiplied by 2 is 18. When I put a -2 in, we'll look at just the x squared. -2 squared is 4, but then we're taking that, we're multiplying it by that coefficient of 2. 4 times 2 is 8. When I put a -1 in, -1 times -1 is 1, and then I multiply it by 2 for our function, 2 equals x squared, and I get a 2. When I put a 0 in, 0 times 0, we're right here, 0 times 0 is 0, but then I multiply that output by 2, I still get 0. When I put a +1 in to my function, 1 times 1 is 1. 1 times 2, because I then have to multiply it by the coefficient of 2, and I get 2. When I put a 2 into the function, 2 squared is 4, times 2 for the coefficient, and I get 8. And you can see the pattern. As x increases by 1, there's a pattern with the y values, those outputs. So when I put a 3 in, 3 squared is 9, and 9 times 2 is 18. So we are going to plot these points. What I'd like to do is I'd like to plot the parent function of y equals x squared. And again, you should be able to do this fairly quickly. When we put in these values for x, -3, -2, -1, 0, 1, 2, and 3, we get the outputs that I plotted. I'm going to try this again because that is just not going to be good enough. So I'm going to try and make this as nice as possible. And I'll come in from the other side of the parabola where it's decreasing. There we go. A little bit better. And I might have to clean it up just a little. There we go. So there's our parent function for y equals x squared. And what we plotted was y equals 2, or what we calculated in blue was y equals 2 times x squared. So we're going to take our x squared and multiply each output by 2. And what we found was when we put a -3 in, we get an 18 out, which is not on our grid. When we put a -2 in, we get an 8 out, which is on our grid. When I put a -1 in, I get a +2. When I put a 0, I get a 0. When I put a +1 in, I got a 2 out. When I put a +2 in, I got an 8 out. So what happens is that this parabola really becomes tall and skinny, very much like the absolute value function. Now, it's not the shape of an absolute value function. This right here, and I am going to fix this because I want you to be very clear on the fact that this is not a V down here. This is definitely a curve. It's just very difficult for me to draw it with this tablet that I'm using. But it's definitely a curve. It is not an absolute value function. But it gets tall and skinny like an absolute value function that undergoes that same factor multiplication out front. So what happened to our function? Well, that 2 multiplying by 2 multiplies x squared by 2 results in each output of the parent function being multiplied by a factor of 2. And if I wanted to be real specific, this right here multiplies x squared by 2. That's, I could have said, when the coefficient of x squared is 2. See, there's your 2x squared. That's your coefficient. So that's a good reminder from the first couple of units. What happens is that we end up with, some of us call it tall and skinny, but technically this is a vertical stretch. So our graph undergoes a vertical stretch. Okay, let's try another one. We have y equals 1/2 x squared. My coefficient see what we have here. My coefficient is 1/2. And what that means is each output of the parent function x squared is multiplied by a factor of 1/2. So I'm going to pick the same values, -3, -2, -1, 0, 1, 2, and 3. So I pick the same values that I have been picking for my inputs. And I know that my parent function is x squared. When I put a -3 into my parent function, I get a 9 out. When I put a -2 into my parent function, I get a 4 out. When I put a -1 into my parent function, I get a 1 out. When I put a 0 in, I get 0 out. When I put a 1 in, I get a 1 out. When I put a 2 in, I get a 4 out. And when I put a 3 in, I get a 9 out. Now, what is going to happen is I'm going to have to go a little bit further. I put the -3 in. -3 squared is 9, but then I have to cut that value in half. When I cut 9 in half, I get 4.5. When I put the -2 in, I do the -2 squared, which is 4. Then I have to cut that in half, and I get a 2. When I put the -1 in, -1 squared is 1. I cut that in half, and I get 0.5. When I put a 0 in, I get 0 squared is 0, times 1/2 is still 0. When I put a 1 into my function, 1 squared is 1, multiplied by 2. Multiplied by 2 is 0.5, which is 1/2. Not multiplied by 2, multiplied by 1/2 is 1/2, or 0.5. When I put a 2 in, 2 squared is 4. 4 times 1/2 is 2. And when I put a 3 in, 3 squared is 9. 1/2 times 9 is 4.5. So I'm going to plot my parent function again. -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9. Now you should be getting very good at this. We've talked about this. I think I keep repeating how well you should be getting at this. Now I'm going to plot my points, -3, 4.5. Oh, you can see that this time we're on the outside of the parent function. Let me go back for just a minute. When I plotted, my parent function was the green, just like it is on the current screen. When I plotted my very first point, -2, 8, which was the one that I could plot, that first point was -2, +8. That was on the inside of the parent function. Now this time the parent function again is green, but this time I'm plotting my point. That first point is on the outside. Let's see what happens with the next few points. -2, +2, again it's on the outside. -1, 1/2, 0, 0, 1, 1/2, 2, 2, 3, 4.5. And I wonder what would happen if I put a 4 in to this function. So if I put a 4 into this function, well, let's see. I put a 4 in. 4 squared is 16, but then this had a coefficient of 1/2. So 1/2 times 16 is 8. I can actually plot that point on this grid. So 4, 8. I'm going to reflect that over the axis of symmetry. Let me highlight for you the axis of symmetry so that you keep seeing this. This is your axis of symmetry right there. When I reflect that point, 4, 8, over the axis of symmetry, -4, 8 is also going to be a part of this graph. And this is no longer a normal parabola, nor did it become tall and skinny. Some people might say that this became a fat or a wider graph. What happened here was we had a vertical shrink. So this is a vertical shrink. Now, something caused us to have a vertical stretch. And something caused us to have a vertical shrink. I'll let you think about that.